right, got that. Okay, so last time I think we left off on 29.4. Do you remember that? So we're going to start up this time with 29.4. I'll get some markers here. And don't forget, I said we were going to answer test questions at the in class today. So my thought was we'd probably spend a little over an hour on this, take our break, and then do test questions to finish the day. That way I'm not stressed out about getting through the new stuff. I discovered in the earlier class we did questions first, and it just made me tense because I was up, not sure. Let me hit the pause button here. We're going to start with this. There we go. All right. So what did I say? 29.4. Okay, 29.4. And in particular, let's see, one for blue. Okay. And we used, what was it, green for 2. So we have 3 currents like this, and then there's some point over here. Point P. Now, in this case, I want you to think of these. I don't want you to think of these as points. I want you to think of them as infinitely long wires. Okay. So in this problem, there's a wire that's sticking out of the board and into the board infinitely far. This particular wire carries current into the page. This one carries current out of the page, and so does this one, I think. Did I get it right? Yes. Okay. Now, there's no wire over here at P, but our goal is going to be to figure out the magnetic field at this point due to the other ones. All right? All right. Any ideas? Oh, and the problem tells us the side of this square, doesn't it? What is the side? Is it A or S? A. So this is A, and I think this is also A. Canadian's favorite square, eh? All right. Well, okay. Any thoughts? What would you do? Okay, an equation for the B field. What is that? And I'm going to say 2 pi distance in this case. So you said that was the B field of what? That's for an infinite wire. Do you agree? Okay, so he's basically pulling this off the equation sheet somewhere. That was the B field of the infinite wire. I agree with that. All right. So then how do we figure out the direction of B? What right-hand rule? Grab that wire with right hand. Then what? What do you know? With this one, align right thumb in direction of what? Current. Fingers curl in direction of B. Do you remember that? So remember that when you have long straight wires like this, if I grab that wire, right, there's 2 ways to grab it with my right hand, right? I could either put my thumb into the page or thumb out of the page. Well, I align my thumb with the B field, or sorry, with the current, right? So that tells me that around this wire, the B field is curling around this way, right? Or this one. going to grab that wire. You see my thumb points out of the page, the same direction as the current. And so for this one, the B field would curl around. Okay, how does that help us? I'm here at this point P. Let's start with I2, just because it's right there. All right. If I start with I2, if I want to get the B field at P, what direction is the B field at P due to wire 2? Which direction is the magnetic field caused by current 2 at this point? It's hard to see. Let me give you another equation. Do you remember that this one came from this equation? This is the BS law, right? And so hidden inside of here is the BS law, and I think this will help. DS is like the direction of the current, right? R is what is R? From what to what? From the source to the point. Yeah, it's always from the source to the point of interest. In this case, point P, right? Well, let's draw that R vector for this wire. Do you agree that's R vector for number 2? From the source to the point? Why is this useful? Do you agree that the output of a cross product is perpendicular to the inputs? And this is true, right? I'm just going to show you here. Let's say DS and R form some weird ass angle like this, right? The B field is always going to be perpendicular. The B field is always going to be perpendicular to it. And that's true no matter how these are oriented, no matter what the angle is. The output of this product, output of this cross product is always perpendicular to both inputs, or the plane defined by both inputs, regardless of the angle between the inputs. All right. So in this case, why is that useful? Because it tells me the B field is perpendicular to this, right? Well, what is the plane defined by the inputs? Well, this current, I wish I had another green, and I do, right? The idea is here is DS, right? This way. Here is the R vector. So what is the direction left for the B field? What are the possibilities? Left or right. So we know it's either this way or that way. That's where this grab the wire comes from. Up above, notice my fingers are going this way. Over on this side, notice they're going down. Down here, they would point this direction. So that's what tells us B2 points this way. Did that make any sense? What I like to do, this is going to seem a little bit crazy here, I like to hold my hand in this very particular way. Look at my fingers, my knuckles, I try to keep my fingers straight all the way to the last knuckle as much as I can. The idea is my thumb is my current, the hand itself is the R vector, and then right here is the B direction, right? See it? That's me, right? So I'm thinking this is the R vector, that's the direction the B field points. Is that helping? Now remember, a good right-hand rule trick for you guys, rather than trying to do that, rotate the paper under your hand on test day, right? Rotate the paper under your hand. Okay, well, let's do 3. I see I3 sitting here. Which direction is the R vector for number 3? Positive I-hat direction, right? So there's R3. What direction is the B field?
Isn't it downward?
I line my thumb up with the current. My R vector extends along the hand. It's up. Did that make sense? Why, Christian? You got it?
Yeah, I got it.
Yeah, so, all right. How about I1 up there? What's the first thing that I've been drawing every time? That's going to be R1. I guess I should draw this, right? All right. So what direction is the B field going to point for this one? Diagonal which way? Diagonal. No. Where do you align your thumb? Yeah, you got to align it there, and notice as it gets around to this plane, you see it's going down left? Because this one, the current was flowing the other way. If the current was this way, then yeah, you'd be right. But because the current is into, is everybody okay with the direction of the B field? You think this B field is going to be bigger or smaller than 1 and 2? 1 and 2 should be the same size, same current, same distance. But what about this one? Bigger or smaller? What? There's more distance. Is there also more current? Which factor is dominant? In this case, they have the same exponent, right? They're both to the first power. Which one is increased more? The distance or the current?
It'd be the current, wouldn't it be by a factor of 2 over root 2?
Yeah, so the current is doubled, the distance is only multiplied by root 2. So he was saying, wouldn't I get a factor of 2 over root 2? Absolutely, that's bigger than 1, right? So it's 40% larger here. Now, it kind of looks wrong, my angle, sorry. It should be at a 45, do you agree? I don't know if that looks right, you can tell better than me. This is B. Oh, shoot, did I mislabel this one? That's B3, isn't it? I think I misspoke. I wrote, or I don't know what I said. So I apologize here. That's B1, right? Okay. And to be honest, you might just care about the directions of these things. And you wouldn't care about the size of the arrows. We just kind of know, oh, there might be some cancellation here. Do you agree? All right. Now, in this case, where are we at? I forgot. Oh, I think I said 45 degrees. Is everybody okay that this was a 45-degree angle here because it's square? So then this would be 45, this would be 45, and this angle right here, wouldn't that also be 45 degrees? Okay. And if we wanted it, we could get this angle right here is 135 degrees. So we know everything about this at this point in terms of the direction. What is our goal in this problem in 29.4? What are we trying to figure out? The net B field. Well, what's the net B field going to be? What's that? The sum of all fields. Sounds like a bad Ben Affleck, Morgan Freeman movie. My mom and my sister were so upset with me one year. It was 4th of July. I'm like, I don't want to see those stinking fireworks. Let's go to the movies. And the movie we watched was The Sum of All Fears with Ben Affleck and Morgan Freeman. I don't know. And I still remember it to this day because my mom was just like, what's that?
You want to borrow it? I got it.
Oh, you got it? No, I'm good. I've watched it a couple times since, you know. It just cracks me up every time. I guess I get some small pleasure out of irritating my mother on 4th of July. I don't know. What's up, Mom? I'm going to Disneyland on live stream, crappiest lecture ever. All right. Next, okay, do you agree we should just get the net field by adding up some vectors? Well, do we have all the information we need on this board? Do I know the directions? Yes. Do I know the size of these fields? What equation could I use to get the sizes? This one. And so I hope this vaguely reminds you of, say you have a couple of point charges and you get the net electric field. Now it's, you have a, instead of point charges, you have a couple of infinitely long wires added up to get the net field. Well, I'm just gonna draw that over here. Let's go to board 6. There we go. So I'm gonna try and draw this one. We just said there's some B field this way, B2. We know there's a B field upwards, that was B3. And then there was one that was off at this 45 degree. It was a little bit longer. Somebody said the net field should be 0, right? Is it possible that it's 0? Absolutely. Is it possible that it might be non-zero? It depends on how this length compares to these two. You agree? So, but do you agree it should be close to 0? It's probably either going to be equal to 0 or close to 0 because this one's probably going to cancel out most of it. All right, let's see if it's exactly 0 or if it's non-zero in this case. Now, if you recall, let's get the magnitude of these fields. So we started with B2. I'll just write that up here. What is the magnitude of B2? Let's go back over to the previous board. Right? I need mu naught I over 2 pi distance. What was the distance for wire 2? A. So it's mu naught I over 2 pi A. The distance for this one was A. And then what's the direction? What was it? The R vector for 2 was negative j hat. The B field was in the positive I hat. Okay. What do we say? Plus I hat. Now, the B field for, oh shit, it's right there. The direction of it's right there. Oh my goodness. Well, do you agree this one was the same size but a different direction? All right. So now we're stuck with B1, the hardest one here. Well, in this case, it's mu naught. What was the current for number 1? 2I was the current for number 1. All over 2 pi. What was the distance for number 1? A times the square root of 2, right? If you recall, we're sitting on a square. The length of the main diagonal is square root of 2 times the side. So if this is A, this is root 2A. And that's why someone said, oh, it's the same times 2 over root 2. What was the direction? What is it? No. So it's kind of right. This is what, so watch out. What I'm about to write is incorrect. A lot of students just say, oh, it's minus I hat minus j hat. But remind me really quick. What's the magnitude of this? If you go 1 down and 1 over, what's the length? Root 2. This is not a direction because it's not a unit vector. This is a unit vector by itself. This is a unit vector by itself, but this together doesn't have length 1. So that's not right. I want you to think this one extra step in here. It's cosine theta in the I hat plus sine theta in the j hat, and then we might have plus or minus signs here, if you know what I mean. And this way we'll get the right answer, okay? So in this case, what's the angle that we had right here? Okay, so we could say if you plug in 45, we have to manually plug in the plus minus signs like we did in 110. So it would be minus cosine of 45 degrees in the I hat. How about in the j hat? What would I write? Oops. Do you agree it's not I hat plus j hat? I agree. And or, you know, whatever. So notice, what is cosine of 45? I'm going to write it in a physicsy way. It's just negative 1 over root 2. The reason I do that is because then I can see this root 2 and that root 2 will combine to cancel that 2. Right? Just lazy. This is not math form. This is what physicists do all the time though, right? They always write 1 over root 2 because they know the root 2 is going to cancel something else later. All right. So out of all that, you see that you could factor it out. The direction is 1 over root 2 times negative I hat minus j hat. That's the difference. Cool. All right, so when I do that, you see this root 2 is going to combine with there. What do we get for this one? The root 2's combine to cancel this. So that's B1. What do you get when you add these three up? 0. So this one is 0. Now, keep in mind, this is a little bit different than point charges. Point charges, do you remember there was like an R squared down there? So for point charges, the field at the corner of the square didn't drop out, even if you doubled the other one. So magnetism and electricity are a little different, but the process seems pretty similar once you get to this part. All right? Oh yeah, wobbly. So far, so good? All right. There's another good one for you to try, 29.7. You could try that one on your own. I think basically you could redo this problem again and make sure you got it on lock. But if you look at the old practice test, there'll be some in there. Keep in mind, the stuff that we're covering tonight is not on your test on Monday. This is all for the following week. So when you finish your test on Monday night, you can immediately start doing your physics homework for this if you want. All right. You ready to try another one? Let's try what we did last time and see if you actually know what you're doing. Let's try 29.8. Okay, I'm going to erase the board and get to 29.8. Okay. So you guys, it's going to take a minute. Go ahead and try to do it. You can talk to your neighbor or you can put stuff in the chat for each other in the Zoom people. Good. What did I say? 29 point something? 8? Okay. It's going to take me a minute. That's pretty close. That current flowing in through this side, out through that side, up here, down here. It says these sections go to infinity, I think, right?
Yes, sir.
But not beyond? Okay. So dumb. All right. And this is segment 1, 2, 3, 4, and 5. All right. Now, there's a point here. This is P. And we're told that this distance right here is radius over 2, I believe. Furthermore, we're also told that this distance right here is A. All right. And part A asks us to relate R over 2 or radius to A or something, right? How would we relate the radius to A? Triangle. So this side is A, this side's R over 2. What's the relationship? What's that? Oh, isn't this a square? If this is a 45, and this is a right angle, isn't this a 45? So how does this relate to that?
Are you able to zoom in on that board?
Oh, yeah, shoot, I forgot. Thank you, I was erasing.
Thank
My
you.
bad. Thanks for speaking up. That better?
Much better.
Yeah, definitely speak up anytime on that. I always forget that stuff. Okay, yeah, so we're asking, how does this relate to that? Give me a relationship between this side and that side. What's that? Oh, man. We just did this on the last problem, didn't we? It's the main diagonal of a square. Yeah, isn't this side equal to that times root 2? Yeah, that's all. I wasn't trying to mess with you guys. Just that, right? Do you agree that we have a relationship between R and A now? This is useful because anything in the problem that has an A in it, I could rewrite in terms of R. Or vice versa, anything that has an R in it, I could rewrite in terms of A. It was just that, nothing fancy there. You could also use, right, sine, right? Isn't sine of 40, or whoops, sine of 45 degrees, we'll use this one, equals A over R over 2. Is that what you were trying to do? If so, that's also a great idea, right? Well, then cross multiply R over 2, that's square root of 2 over 2 equals A. You get the same result. Same thing when you clean them up. All right, nothing fancy. So I'm going to, just to ensure we have maximum room, we said that root 2 times A equals R over 2. All right, what's part B? Direction of the magnetic field at P. What do you think? Any guesses on that? How would you do it? Okay, maybe it's not obvious. Let's come back to that. I realized this in the earlier class. Maybe I should have asked part C first. What does part C say? Okay, so it's asking, are there any segments which produce 0 contribution? What's that? 2 and 4. How do you know 2 and 4? Okay, let's start. What was the equation for figuring out B fields from wires? What's the one thing that we keep saying? It's a lot of BS. U naught I over 4 pi integral of ds cross r vector over r cubed, or r hat over r squared. That's our Biot-Savart law, right? Why would segment 2 give us 0 contribution? What would ds look like for segment 2? Maybe something like that. Do you agree? What would the r vector look like for segment 2? ds points this way. The r vector points this way. What's the angle in between? 0 or 180, depending how you want to think about it. I would say 180 because these are anti-parallel. What do you get when you do the cross product of things that are parallel or anti-parallel? 0. Do you agree that for this segment, you were absolutely right? In this case, right, when it goes radially away or radially towards, there's no magnetic field at P. Does this wire create a magnetic field? Yes. It creates a magnetic field over here. It creates one here, here, just not at any point right over on this line. You see what I'm saying? Similarly, 4 is not going to create any magnetic field on this line. Good? So that's something you should know. Now I need to erase these here. Well, actually, I think I can leave those out. So in this case, segments 2 and 4 produce no field, right? That may help us get part B, because now we know we don't need to worry about those segments, right? How do you get the direction of B1? So I'm going to write B1 hat here. What does B1 hat mean? The direction of B1. This is not the field, this is the direction of the field, B1 hat. How do I get the direction from a straight wire? Grab that wire. Is that looking good? No, why not? Okay, so is that looking good? No, why not? Left hand, I was trying to mess with you. Okay, good, good. So there we go, right? So it's out of the page, right? Up here, is that the point I give a shit about? No. So I got to do it that way. That's headed towards P. You agree? So this one would be probably, do you agree we usually assume this is I hat and J hat? So then this would be what? Negative K hat. What about B5? Hat. Same or opposite? Same. We don't, yeah, all that matters is basically if you have a straight wire, are you above or below it? Or are you on the left or the right of it? Okay, so that's negative K hat. What about B3? Hat. What's the right-hand rule for that one? Does anyone remember? What is it, Christian? Come on up. Yeah, sucker. Come on up. Stand over there. Okay, he's gonna get out his right hand. Class, let's give him a round of applause here. Okay, so now what are you trying to do to figure? We're trying to figure out the direction of field 3. Agreed? Okay, where do you put your right hand? He's curling it with the current, yes. And so what way is your thumb? So what direction is the field from 3? Yes, let's give another round of applause there. Thank you. All right. That's it. All right. G, what direction is the field at P? Do you agree it's going to be in the negative K hat? All 3 contributions point in the negative K hat. Now, if one of these was going the other way for some reason, we wouldn't know and we'd have to do all the math first. But in this particular case, it's basically right-hand rule. We see they're all negative K hat. We expect the net field direction is in the negative K hat. Isn't that hat vector kind of nice to save you a lot of writing? You don't have to say the direction of B1, the direction of B5. That's what this sentence means. The direction of B1 is into the page. Just less writing. All right. What's part D? We now know the direction. Part D says get the magnitude of the magnetic field at P. All right. Any ideas what I should do? What's that? Wait, just tell me what I should do in terms of these, that each segment produces a B field. If I want to get the net field, what should I do? Add them up. We'll start there. You're ahead of me. Sorry, you're already. Is that valid? Why is this wrong? You have to add, you can't just add magnitudes to get the magnitude. You have to add the vectors and then get the magnitude at the end. One of the most common mistakes is people say, oh, I'll get the magnitude by adding up the magnitudes. And you know that doesn't work, but you're in a hurry on test day and you blank and you do that. And it's just so frustrating because you lose points. All right. Which B field is the easiest to compute, in your opinion? We've got three of them. We got 1, 5, and 3. This is an odd problem. What's that? Oh, wait a minute. This is wrong, isn't it? Actually, it's right if I just add in this. And then these two go to 0. I was just testing you. Oh, sorry about that. Is that better? Does that look better? I apologize. I just didn't finish. Yeah, that's dumb. I got too excited. Yeah. All right. So which of those fields, 1, 3, or 5, is the easiest here? Go with your gut. I'll tell you if you're wrong. 5. Okay. 3 is the easiest. Why is 3 the easiest? What's that?
So basically we did the last problem, sine data plus or minus.
That was for a straight wire. Is this a straight wire?
No.
No. What was our trick for curved wires? How much of a circle is that? Isn't B3 equal to 1/4 of B circle? And then we know the direction was something down here. What was it? Negative K hat. Oh my gosh, in this weird problem, you could actually just add up the magnitudes and get the answer right. Do you agree that with this problem, because everything's pointing the same way, this is like the one exception. You could actually just add the magnitudes and get it, but we're not going to do that because it's a bad habit. What was the B field of a circle? Does anybody remember how to get that from your exam equation sheet? Yes, that's the memorized result. Is that on the equation sheet too? Look at what's the B ring on axis there? Isn't that?
U naught IR squared over 2 times R squared plus 2 squared.
Got it. This? That was for ring on axis. Well, if we're at the center here, what's our Z value in this problem? 0. So remember, if Z equals 0, what result do we get? Exactly what he just said, U naught I over 2 times the radius. Now wait, in this problem, is our radius little r?
Yes.
Okay. So notice here, little r is equal to big R in this particular problem. Is that good? All right. So I think we could just plug this into here, and don't you get 1/8 for B3? 1/8 mu naught I over R. Because I got a 1/4 here, and then there's a negative K hat. So far, so good. So now the harder part is 1 and 5. And maybe it's not that hard. I don't know. I don't think it is, but it's slightly harder, I think. Everybody good with 3 though? Good on 3?
You show where the R squared is?
Oh, this is to the 3 halves. So when you put a 0 in here, it's R squared, square rooted cubed. And so that gets an R, yeah, so you get an R cubed in the basement. Is that it?
Yeah.
Yeah, for sure, for sure. And so the reason I wanted to do it this way is I believe this is the one I put on your equation sheet. So you have to know if you're at the center of a circle to set z to 0. All right. All right. Okay. What do you guys think about 1 and 5? How do you want to attack 1 and 5? Anything you think? What's that? There's a shortcut. Okay, so I'm going to redraw this over here. Let's get a new page. Which one do you want to do? 1? Okay. So here's wire segment 1, current flowing to the right. And then our point P is right here. You said the shortcut. What was the shortcut? Okay. Give me a second. This was what we derived last time. Remember that? Okay. Come on up. So do you agree we already figured out the direction for this one? So we don't need the direction. We just, if you want to use this formula, we need to know the angles. So what would you do for these angles? Do you remember it all?
Well, I know I'm gonna get an angle, but there's an angle here.
Okay. What's the first thing you do with any straight wire segment in your checklist?
Oh, the.
Draw that.
We draw that.
Yes, that is perpendicular to the wire, even though, so scoot over for a second, right? Even though the wire doesn't go there, that's where you have to draw the perpendicular bisector. So, right, that, okay, good. So let's draw a right angle there. Big enough for the back of the room to see. All right, good enough. You can see all right? All right. So now what are our angles? Not that.
This one.
It's the angles at the point P. So it's going to be this one. Now they're not going to see that in the back, right about there. Okay, and what is this angle? Do we know it? What is it? 45, right? So let's put a 45 right there. Yeah, it's tricky because you got to be able to read it in the back of the room. Sorry, I'm picky. There we go. Yeah. Yeah, it's different on the whiteboard, right? You guys can see it. All right. That's one of the angles. Is that the initial or the final? Is that the starting point of this segment or the ending point, in your opinion? Ending. Do you agree it doesn't matter really? Because we're going to get the direction separately, right? This is just to get the size of it. So let's call this the end. You mind if what you're telling me here is this is theta final equals 45 degrees, right? I actually would call that negative 45. Because do you remember what angle I called 0? Straight up. So this was theta equals 0 degrees, right? And so now I'm going to erase this because we got it into there. Cool? Is everybody cool with that? Okay, where's the other end? Where's the other end of the wire? No,
Oh,
we're just, yeah, how far out?
it's infinity. So.
Yes, yes, it's way far out. So act like you're trying to get to my finger right here. Try and draw this line. Yeah, and then if I could, this angle right here is approximately 90 degrees. Agreed? Let's give him a round of applause. Very good. Actually, it's not 90. What is it? Negative 90 because we're on this side. Don't you love that? And that is important. It doesn't matter whether you call them 90 or 45, but here they're both on the same side as 0. So you should call them both positive or both negative. Does that make sense? All right. So in this case, I would say theta final is negative 45 degrees. Theta initial is negative 90 degrees. Okay. Now, out of all that, let's get the number for this. Well, mu naught I over 4 pi a. What's sine of negative 45? Negative 1 over root 2. This is physics, you can get away with that. And then what's sine of negative 90? Negative 1, right? Watch out. This is why it's so crucial to get the signs the same. Right? In this case, we're not getting the whole infinite wire. We're not even getting half an infinite wire. So our field should be less than a half infinite wire. Do you agree? Right? We aren't making it all the way to here. We're missing out on the biggest part of the wire. So this should almost cancel out, and it does. Now, in this case, can somebody give me a decimal for all that junk? I'm going to get out my calculator. Race it. Okay, so inside, it looks like I'm going to get 1 minus 1 over root 2, right? 1 minus sine of 45. Okay, and then I need to divide that by 4 and divide that by pi. I got 0.0233. Remember, it's negative 1 over root 2 minus 1. So this is right.
Negative.
Is that what it was? Minus a negative?
Yes, sir.
Yeah. See if you get that. Double check my work.
Yep.
You're getting that? It was good. Okay. All right. So we figured out the B field from what, right? So is everybody happy that that's B1? I'm not.
Negative K.
Negative K hat. We talked about the direction earlier. Because I snuck that arrow in on you, you got to remember to stick it in there. Yeah. So in this case, I'm just going to write that result up top. Usually we write the numerical coefficient out front. And then what did I forget? K hat? All right. All right. Well, we're almost there. What's B5?
Shouldn't it be the same thing?
Is it the same or is it opposite?
Or
Let's go back and look. I've forgotten.
I think it's the same.
It is the same. Didn't we say they point the same direction?
Yeah.
And think about it. Isn't this basically like all part of one infinitely long wire that's just got a chunk missing? So this should basically all be the same way. So you're right. It was the same. I was testing you. For once, I was actually testing you for real instead of just screwing up. So how do we get the net field? Couldn't I just say 2B1 plus B3? Huh. So this is 2 times that. Well, I'm just going to write that 0.0466 mu naught I over A. And what was the other one? 1/8, which 1/8 is 0.125 over R in the negative K hat, right? Huh. Why did we have to do part A? This is a dumb way to write it, isn't it? Because isn't there a relationship between R and A? What was that relationship? I forgot. So R is equal to 2 root 2 times A, I believe, from part A. So now you know why that's useful. The circular formulas are written in terms of the radius, whereas the straight wire formulas are written in distance along the perpendicular bisector from the wire. Ah, joys. So there's still a little bit of work to do, but then you could combine the two and answer it the right way. So I'll just say finish it up at home. You got the solution. You can double check you have the numbers right. Cool. What do you think about that one? Making some sense? All right. Is there another way we could have done segments 1 and 5?
Yeah, we combine them.
What do you mean combine them?
There, because consider just relative, it's not-
Whoops, let me go back to this board. Say again.
maybe that's not- They're the same, I was thinking.
Okay, so make one megawire. And you could just get the B field is mu naught I over 2 pi times A. That's the field from an infinite wire. And then what?
Add to what,
Subtract.
close to that.
We could take off this part. Is this showing up on Zoom? Yeah, it is. Okay. The idea is you could do an infinite wire minus this part. Whatever you want to call that. Right? But then you could do from negative 45 to positive 45 to get that segment. But either way, you're going to have to use that sine theta shortcut formula. So you either have to do this one and double it, or the whole straight wire and subtract out the chunk that's missing. Is that good? So depending which way you saw that one, those are different styles. Should get the same answer. All right. One of the things that's frustrating for students in this part, just because a wire is infinitely long, doesn't mean you could use the infinitely long B field, right? Infinitely long just means goes to infinity, one of the limits is infinity. So you have to be careful when you're doing these Biot-Savart law problems. Remember, if it goes to infinity in both directions, it's infinitely long. If it goes to the perpendicular bisector, we call it half infinite. And then these are just some other weird, it's not half infinite, it's close to half infinite, but not quite. Got it? I don't know if you noticed this over here, going back to this page. Right here. This number was about 30%. Do you remember that? It was 0.29 and change. So we could see that actually, in this case, if this segment is 30% of it, and this segment is 30% of it, how much is left in the middle? 40%. So it turns out this tiny little segment here matters more than either the left side or the right side, which are infinitely long. Isn't that crazy? It's because most of the field comes from points close to the perpendicular bisector, right? These are the points that are closest to the wire. So these portions of an infinite wire would contribute the most, 40% of it, in fact. Kind of cool, right? Or maybe not, I don't know, it's just slightly interesting to me. Whatever. Most of the field strength comes from the middle section of the wire. That's what I was trying to point out, nothing more. Okay, when you're far from the ends, it doesn't matter that much. All right. All right, I feel like that's pretty good. Take a look at 29.9. Okay. Oops, 5, there we go. If you look at 29.9, that's ones where you can practice your circles and straight lines and figure out which segments matter and which segments don't. Yeah, so I'm gonna let you do that one at home, but there's another example of how I did that. Both of those were old test questions, so you can see that's kind of like how I like to phrase things on test questions. Again, this is not on the test on Monday. It's on the test 3, the Monday after Thanksgiving. But, okay. And now I need to erase, and I'm gonna let you do that one at home. I want to talk about 29.10 right now. All right. The idea 29.10 is supposed to look like this. You see this thing right here? I've got a plus terminal of the battery, and I'm going to connect that up here to the top, to both of these wires simultaneously. And now down here at the bottom, these two wires are connected to the negative terminal, right? And this is bridging them so they're connected together. So the idea here is, I think in this one, the current would flow down on each side. Do you agree? So this is looking a lot like the picture that you have in front of you on 29.10. So that's, I'm gonna get started. I gotta erase the board, start looking at the problem. We'll meet back on the whiteboard in a minute here, okay? So I'm just gonna erase for a few minutes. I'm gonna need both boards maybe, so. Go ahead, talk to a neighbor as much as you want, talk in the chat, anything you want, all right? I like this one because it relates to what's on your test on Monday. Part of it. Oh, magnetic fields. What did they say? 29.10? We're gonna have a power supply somehow connected to some wires. We're gonna be connected this way. All right. We know this whole thing has length L. We know the distance between them was X. We have two wires, there's some distance X apart. We know the current. I'm going to use blue for this one, I don't know why. We'll just say I1 is flowing downwards. And we got I2 flowing downwards as well. All right. I think those quantities are known. Okay, so even though they're not infinitely long, maybe if I could show you on this demonstration really quick here. The idea here is these wires are clearly not infinitely long. They're about 40 centimeters long. But the idea is compared to the spacing between them, this length here is much, much longer than the space between them. So in that, if I was this close to them, they would look infinitely long to me because I can't see the top or the bottom, all right? So everybody cool on why these are infinitely long? It's this length is large compared to that length. Okay. Okay. What's the B field created by 1? Okay, come on up, Jesse.
Oh.
Yeah, you don't want to come up? Come on.
I'm not even positive I'm right.
What's that?
I'm not even positive I'm right. All right, well, I better learn it anyway, so.
Yeah, exactly. You learn more by coming up. Okay,
Alright.
so,
Thumb down
yep,
and curl it, so.
yes. So on this side of the page, which direction is the B field? So right here, okay, so this is wire 1, right? Here, you got it.
Yeah.
What direction is the B field right here then?
Shouldn't it be?
Yeah, what's that way?
Okay.
Yes, out of the page. Let's give him a round of applause. That was it. Okay.
I was right. though.
Oh, man, come on. You gotta give him a better round of applause. than that.
No, I'm good, I'm good.
Yeah, there we go. Man, come on, that's cold. All right, so. Out of the page. Is the B field going to be uniform in strength, or will it be changing? Does anybody know an equation for an What is it? 2 pi. So it's 2 pi a for the infinite wire. It's 4 pi a sine theta for a segment. Got it? And so when you plug in sine theta equals -90 and +90, you get a 2 because it's a 1 minus -1. And that's why this one has a 2 pi and the other one had a 4 pi. Good? Yeah. All right. So what does A mean? Distance, what distance? Distance from wire, right? Okay. Well, is that a constant as we go over this direction? Is the distance from the wire constant as I go away from the wire? No. So where would the magnetic field be strongest? Close to the wire. So as I scoot over, the B field should get weaker, agreed? What would be true about the B field on this side? Into, but it would be the same size because it's still close, right? But as I go away, wouldn't it get smaller? And then smaller still. That's the B field from 1. It's large, close to the wire, it's small far, and it's curling around in this weird way like this. Okay. Oh my goodness. That made me just. My next question is, what direction is the force on wire 2 due to the B field created by wire 1? That's a lot of words. I want the direction of the force caused by something on this one, right? It was caused by wire 1 on wire 2. Agreed? So here's the deal. In the previous chapter, chapter 28, we kept talking about forces on a wire or whatever. And there was some B external. Remember that? Now we know where B external might come from. This wire creates the field that is external for the other wire. So B1, this field that we keep drawing here, is going to be the external field that causes a force on this wire. So help me out. What was the equation for force on a wire? From the last chapter that you're being tested on Monday. What is it? You said QV cross B external. That's close. I don't see current in there. Do you? It was the I. And then you had to integrate, right? That was the equation we're trying to deal with now, right? So you're right. Well, now tell me, what is the current? Is it current 1 or current 2? We're looking for the force on wire 2, right? So I should use the current of wire 2. This is going to come from wire 2. Agreed? That's the current that is having a force exerted on it. What's the external field? B1. You see what I'm saying now? And now you know why I kept writing B external all the time, right? It's from some other source. You could have current in this wire causing, you could have current in this wire causing a field on, or causing a force on this wire. All right. Now, we're going to have to integrate this one, right? Do you agree the B field is non-uniform? Do you agree the B field is non-uniform? So do you think we're going to need to integrate?
I'm saying yes.
No. Okay. Why? It looks like you think, right? What's true about the B field at every spot on this wire? It's always the same distance away. So even though the B field is non-uniform, along this wire, the B field is uniform. Do you agree? So that means I don't need to do all that. So give me another equation that's better. That will work in this case. Do you agree? In this case, yes, the B field is non-uniform, but it is uniform along the length of the wire in the direction the current is flowing. Check. Does that make sense? My gut, when I first saw this, was like, oh crap, I'm gonna have to integrate. And I'm like, wait a minute, it's uniform just along that length. That's what I was trying to point out. All right, I think we can plug in some stuff now. Well, I'll do the first part. The current is I2. Done. What's the length vector? What's the size of it? L is the size of it. What is the direction of it? Yeah. So this is negative L J hat crossed with, what's B1? At this position, what is B1? U naught 2 pi x. In this case, the distance is x for this segment, for this segment, for this segment. So the B field is the same. That's not enough. Because it's, what did we say it was? K hat? All right. After all that, what do you get for the force that wire 1 exerts onto? Let's go. We're going rogue. The caps are off. Okay. What do you get out of all that junk? Yes. Oh, wait, what's I here? Isn't that I2? Yeah, maybe I should say that's I2. Sorry about that. No, that's not I2. That's I1, because that's from B field 1. Sorry about that. Oh my gosh. So out of all that, mu naught. No, I'm not even going to use them. 2 pi x. What's the direction?
No, it's not. It's either negative.
J goes to K goes to, and then there's a minus sign, so it's. So what direction is the force on wire 2? To the left, negative I hat. One exerts a force to the left on 2. What direction is the force exerted on 1 by 2? What direction is the force on 1? What's that?
So I have to,
Yes, how do you know that?
just the opposite, basically.
Why? Why is it the opposite?
It's negative.
Give me a law.
Ooh.
Newton's
Oh.
third law. 1 exerts a force on 2 to the left,
So, oh, yeah, that's the right.
so force of 2 on 1 is equal in magnitude and opposite in direction. Gotcha. So, all right, questions out there from Zoom land? You got it? The caps are off. How about in here? Any questions on that? That's a lot of work to see these 2 little wires. Well, at this point, I think it's important before we do the demo to actually do some math and plug in numbers for once. You wouldn't think so, but I think it's important. Look at part, let's just skip to part F. Let's say we know these dimensions. So our length is equal to 40.0 centimeters. What's our X value?
3 centimeters.
And then what else do we have?
I1 equals I2, which equals 37A.
Oops. 37 amps? Is that a large current or a small current, in your opinion? That's a big current. That's fire starting, right? Think about it. Usually we're dealing with like 37 milliamps in lab, right? So this is 1,000 times larger than our average currents. Plug in the numbers and see what you get for this force. Punch them in. And let's just get the magnitude of it. So the force mag. I'll punch it in as well. So we got, what was mu naught? 4 pi e negative 7 times 37 squared, because it's in there twice, I1 and I2, times 0.4, right? 40 centimeters is 0.4 meters, divided by 2, divided by pi, divided by 0.03 equals about 3.7 milli. Is that a large force or a small force? It's tiny, right? Think about this compared to my number of newtons. That's disturbing, right? I'm 1,000 newtons of Jorstead right here. Just what no one wants, 1,000 newtons of me. But yeah, my weight is about 1,000 newtons. So, I mean, think about this. This is crazy. This is crazy small, right? If we go to these rods right here, whoops, wrong way. And then what I'm going to do is I have a piece of foam core here to help them stand out. You can see them better. Can you see that better now? Okay, so we got these two wires here, and I'm just going to get this one out of the way because it's distracting me. I got to remember to plug it in. And then nothing up my sleeve here. There's a power button right here. So when I do this, I'm going to energize it. Now let's think about this. 3 millinewtons, right? I don't know if you can see this. Like there's a little bit of friction here. Do you agree? It stops sliding after a while. Just giving it some flex here. There's still a little bit of friction. So I'm going to get these pretty close together. What should happen when I press the button? Current's going to flow downwards. What should they do? Attract or repel? Go back to the board. They're going to be attracted to each other. Agreed? That's our prediction. With a strong or a weak attraction? Weak, despite using 40 amps in each wire. Okay, all that for this. Ready? Did you see it?
No.
So it's so weak, I'm going to get him closer.
Oh, there it is, barely.
And if there's any friction at all, right, it's like enough to, let me try a little closer. It's like, they've got to be so close for this force to be strong enough. There, I saw a move. Did you see that? Oh, they came together. This is not very dramatic. Is there a way we could get more current? Well, actually, we could do this too. Do you agree I could switch the direction? If I switch the direction, what should happen to them? So how could I do that? I'm going to disconnect this from here, disconnect this from here. And now what I'm going to do is I'm going to run it this way. I'm going to connect this one to the plus terminal. So now the current's going to flow upwards in this one, up to the top and then down to the bottom. What should happen to these wires now? What's that? Repel. Let's see if this works a little better. Ready? Here we go. So it seems to be, there seems to be a little bit of, it favors one direction more than the other. Of course, it's a little easier to start with them right next to each other, right? Because then the field is strong right next to each other, so you could actually see it. But here, it's not doing too much. So, okay. Gosh, I wish I could do this with more current. Can you think of a way? What's that? No, screw that. I need some, how do you get large currents? What can you make small to get a large current? Resistance, all right. I could use a low gauge wire like this. Right, and let me just get the demo set up, hold on. Oops, wrong way. That's so annoying. Okay, come on, there we go. All right. So I need something that can produce a lot of current. Can you think of something that produces a lot of current? Automotive. Car batteries, right? So what we're going to do is we're going to take this jump starter, right, which is effectively a car battery, connect it to this wire with no resistance, and this is a low gauge wire. Do you agree we're going to get a shitload of current? That's a technical unit. It's not SI, but it's one of my favorites. Now there's a switch here, right? Now I did use this earlier in the day, so there's a small chance the jump charger didn't get fully recharged. All right. If so, you can hate on the AM class and say they get so much more than most, but hopefully there's enough charge on this. Love me. Stay on this time? All right, so there we go. So now I got this switch, and just so to be clear here, I don't know if you can see this. Whoops, this red wire. Let's do this. This is connecting to the two wires at top, all right? So then both of these are connected together here with a wire nut. So basically we're doing this in parallel. So they're going to be, current's going to be flowing down. So again, do light currents attract or do light currents repel? Light currents attract. That's what we just saw a minute ago. Can you see this on Zoom all right?
Yeah, it looks good.
Okay, cool. All right, so you only get one shot because this is going to drain this thing pretty quickly. Ready? All right, so we expect these to do what? Come together. I kind of want to see it too, so I'm going to come around the front. This is fun. All right. You'll probably see a big spark here. Did you see that? Oh, look at that smoke. Whoa. So that's spot welding, right? That's what I basically, so this switch is going to be destroyed in a couple of years. What if I only use this a couple times a year? Did they come together? Yes. I forgot to watch. I was too busy watching this. Yeah. All right, let's see if we got any more in there. Yeah. Yeah, but it's starting to deplete this pretty quickly. All right, so that's enough on that. Basically, the first one is always the best. And so we see these explained together. Now, wait a minute. How does this relate to magnetic moments and permanent magnets? I want you to think of these. Oh man, they're warm already. Not hot, but warm. So in this case, right, think of these as magnets, right? And the idea was the current's flowing down. So this one's a magnet going this way. This one's a magnet going this way. If you have two magnets, what do they tend to do with their north poles? The north goes to south and the two align. I can't do it. I don't have two right hands, right? All right, Christian, I'm not going to make you stand up and hold hands with me. All right? But the idea is these two, right? The idea is if the fields are spread out like this, right, it's advantageous for them to be as close as possible and overlap and form one big magnet like that. Yeah. So even though this doesn't have a north pole and a south pole in the traditional sense, it's still the same thing as two magnets wanting to snap together. Right? These magnets are pointed the same way in this weird spiral way. All right. Is that good on that? Now it's after 6. Why don't we take our break? Let's do that. All right. And then since just for you on Zoom, I'm probably going to stop the live stream and then start a new one. So when we come back, don't let me forget your